Hello, and welcome to this session. My name is Joanna Cristea, and today I'd like to present the open source framework for co-emulation using PYNQ, or as we like to call it, the OFC. In this presentation, I'm going to talk about what OFC is and why we developed it, which are the principles behind the OFC architecture, what is the integration effort in order to use the framework, and some experimental results, followed by a summary and a few conclusions. As functional verification using co-emulation has been on an ascending trend for some time now, we were curious on how to achieve a co-emulation environment. However, we only found proprietary solutions and no clear way on how to do it in an accessible way. Therefore, we came up with the idea of developing the OFC, which stands for Open Source Framework for Co-emulation. The idea behind the OFC framework is to provide an easier way to achieve a co-emulation environment. When we created the OFC framework, we had several key features in our mind. Firstly, we wanted the framework to be open source, so that anybody can use it. The framework should not depend on any specific simulator. Also, it should be easy to understand and integrate, and anyone should be able to make changes and upgrade the framework. Compared to a simulation environment, a co-emulation environment involves emulating the DUT and part of the testbench on a hardware platform. Obviously, a connection between the host machine containing the testbench and the hardware platform is required. The hardware platform usually contains an FPGA and a processor acting as an FPGA controller. This architecture requires another connection layer between the two components. We now have the host machine, the FPGA controller, and the FPGA side of the hardware platform. To connect the three components, we developed two separate modules which together form the OFC framework: the OFC SystemVerilog Python connector and the OFC Python FPGA connector. For achieving a co-emulation environment, the two modules should be used together, but based on the project needs, they can also be used separately. For example, you can use only the OFC SystemVerilog Python connector if your SystemVerilog testbench requires Python machine learning functions. Or you can use only the OFC Python FPGA connector if you want to create a verification environment using only Python language. Let's have a closer look to what the OFC framework contains. I'm going to present an overview of the entire framework. As I said, a co-emulation environment implies emulating the DUT on a hardware platform. The hardware platform used to develop the OFC framework is the PYNQ board. This board is part of the Xilinx family, where the FPGA controller is called the processing side, and the FPGA is called the programmable logic side. Therefore, the DUT will be translated in the programmable logic side of the board, which means that the usual UVM driver can no longer do its job, as it has no direct access to the DUT interfaces. A new driver is needed, one that instead of stimulating the DUT interfaces, sends the items to the hardware platform. The OFC framework provides such a driver. The OFC driver sends messages containing the items to a proxy component that manages the connection with the hardware platform. This component is called OFC Server Connector and is responsible for initiating the connection with the processing side of the PYNQ board, and also for sending items and receiving monitored results. On the PS side, the framework provides a Python server, which communicates with the testbench using TCP messages. This server receives requests from the testbench and sends monitored items back to the host machine. Because we wanted the framework to be as flexible as possible, we decided to give the user the possibility of managing the way the items are processed within the OFC Python server. For example, the user can decide a different order, or he can buffer a number of items before sending. That's why the OFC Python server is marked as only partially implemented, because the user has to define the way the items are processed in the processing system side of the PYNQ board. The OFC server connector and the OFC Python server communicate through TCP messages. Because SystemVerilog does not offer support for TCP functions, the send and receive functions are implemented in C++ and used within the test bench using DPIC. To connect the processing system side and the programmable logic side, you can use the OFC FPGA connector provided by the OFC framework. This module is based on the PYNQ API provided by Xilinx and identifies DMAs within the design and uses them to send and receive data from the DUT. On the programmable logic side, the DMA modules send data to the DUT through HDL drivers and receive monitored items through HDL monitors. The items monitored are sent back to the test bench through the OFC FPGA connector and OFC Python server, all the items being received within the same component, the OFC server connector. Therefore, the user must define its own OFC monitor, which sends the items through the appropriate ports. As you can see, the OFC provides most of the components needed to achieve a co-emulation environment, and the only things left entirely to the user are the HDL components and the OFC monitor. If you are going to use the OFC framework, you will need to provide some basic configurations. For the OFC server connector, you have to set the hostname and port number of the Python server in order to establish a connection. Also, because there is no way to know when the DUT has finished processing all items, as the test bench is no longer directly connected to the DUT, an end-of-test marker should be provided. This end-of-test mechanism is based on sending a special item at the end of the simulation and waiting for it at the Python server side. After the item has been processed, the Python server should send the end-of-test marker, which will be recognized by the test bench. There are also some optional configurations, such as the timeout before a TCP send or receive action is dropped, default being 1 millisecond, or the delimiter used between items within the same TCP message, default being the endline character. For the OFC Python server, you should provide the port number for the server, and it has to be the same as the one configured for the OFC server connector. Optionally, you can also change the default delimiter character, but you need to make sure that the same character is being used on the OFC server connector side, and you can also configure the buffer size of a TCP message. For the OFC FPGA connector, you have to provide a bit file for configuring the programmable logic side of the PYNQ board. In this way, the OFC can handle the programming of the FPGA side, and it can identify and use the DMA modules within the design. Now, we'll look together on what you need to do in order to integrate the OFC framework inside an already existing test bench. 4 simple steps are required to integrate the OFC framework into your verification environment. You start by replacing the usual UVM drivers with the driver provided by OFC. Then, you create your own OFC monitor. After that, you define how the OFC Python server handles item processing. And the final step is to create HDL drivers and monitors on the PL side of the PYNQ board. As I mentioned on previous slides, in a co-emulation environment, the DUT is emulated in a hardware platform, and therefore the usual UVM drivers can no longer stimulate directly its interfaces. The first step in achieving a co-emulation environment using the OFC framework is to replace the original drivers with the OFC driver. The OFC driver converts items into strings and sends them to the proxy component that manages the connection with the hardware platform, meaning the OFC server connector. You can do so by using the UVM factory override. The OFC driver does not need any additional interference from the user, being a plug-and-play component. The only thing that it is necessary for the OFC driver to work is making sure that the items have a PEG function, as the driver uses this function to convert items into messages. Items may have their fields registered with UVM, or a custom PEG function can be defined. The second step for achieving a co-emulation environment using OFC is creating your own OFC monitor. This step is necessary as all items are received within the OFC server connector, and there is no way for the framework to know where to send those items. The OFC framework has no knowledge about your verification environment architecture. The connector receives messages and splits them into string items based on the delimiter. The OFC monitor should receive each string item and convert it into a sequence item. This may be done with an unpack function, just like in the case of the OFC driver. The OFC monitor is also responsible for sending the converted items through the appropriate analysis ports based on your verification environment architecture. The messages from the test bench through the OFC server connector will be received by the OFC Python server. The server will split the messages into a list of string items and will pass them to a function called compute response that you need to define. This is the third step, defining the compute response function. This function should convert the string items into items that will be used by the HDL drivers. The converted items will be sent to the DUT protocol interfaces using the OFC Python FPGA component through DMA modules. Each protocol has its own DMA module that must be specified when sending data. The OFC Python FPGA module can also be used to get the items collected by the HDL monitors. The DMA corresponding to the protocol must be again specified. The collected items should then be converted into string items and pushed to a list. This list of collected string items should be returned so that the server can send them back to the test bench. The fourth and final step is implementing the HDL components within the programmable logic side. These components are drivers and monitors that can be timed as opposed to the rest of the test bench. The HDL driver should send items to the DUT, accessing directly its interfaces. The HDL monitor should collect information from the DUT's interfaces and convert it into items. These components should be linked to the proper DMA module, so that they can be accessed from the OFC FPGA connector. The PL side connections and functionality can be defined using the Vivado environment, a tool provided by Xilinx. The DMA IP can also be found and instantiated within Vivado. This IP has axis stream interfaces. Therefore, the driver and monitor should have an axis stream slave or master interface. Also, you can export the bitstream file using this tool. Based on the FPGA board you want to use and your preferences, you can also choose another software tool to program the FPGA logic. The OFC Python FPGA component takes care of programming the PL side and finding the DMA modules within the design, given the bitstream file. Before showing you the results of using the OFC framework, I'd like to explain the setup used in these experimental results. The hardware platform used to emulate the DUT and part of the verification environment was located in one place, whereas the simulator was located in another, across town. To connect the two platforms, we used an intermediate machine which forwards packages from one platform to the other. This is actually the main reason we use the TCP connection. Having a functional solution for a co-emulation environment using the OFC framework, we decided to see some co-emulation times. We tested the framework on a design called streaming router that was implemented in-house. The streaming router has one configuration interface, one input interface, and 4 output interfaces. Since the complexity of the design influences the co-emulation speed, we chose to implement a second version of the streaming router by including a data encryption block. The encryption block chosen is an AES block. For the simple streaming router, without the AES block, we tested the OFC using two different configurations. The first configuration implies sending items from the test bench to the Python server whenever possible. From the Python server to the DUT, items are sent through DMA accesses. A DMA access implies an overhead regarding the time consumption, therefore the less DMA accesses, the faster will be the co-emulation process. To avoid as much as possible this overhead, it's better to buffer items and send multiple items within the same DMA access. This number cannot be too great, as resources on the FPGA side are also affected. We chose 10,000 stimuli to be sent, which is an arbitrary number to reduce DMA accesses, without using too much FPGA resources. The monitored items are received back within the test bench whenever possible. The second configuration is different from the first one regarding the timing for receiving monitored results within the test bench. This time, monitored items are buffered within the Python server and sent back only when the duty has finished processing all items. This way, the test bench is allowed to send all stimuli and then receive the monitored items, resulting in fewer context switches. Of course, fewer context switches result in higher performance. For the streaming router with the AES block included, we tested only the second configuration, because it was the one with better results. For the first configuration, on the simple streaming router, with sending and receiving whenever possible, we have the following results. You can see here that the time necessary to complete a co-emulation process using OFC is very similar to the time needed to complete a usual simulation. There is only a slight acceleration for co-emulation. Here, the acceleration factor decreases with the increase of the number of stimuli. That is an effect of having multiple DMA accesses. For example, for 10,000 stimuli, only one DMA access is needed, but for 100,000 stimuli, 10 DMA accesses are needed. For 500,000 stimuli, the FPGA processing time is less than a third of the total co-emulation time or total simulation time. The FPGA processing time was measured within the Python server from the time the Python server is ready to send items to the DMA modules to the time the DMA modules have returned a list of collected items. The FPGA processing time is the sum of all these times. For the second configuration, on the simple streaming router, with sending whenever possible and receiving only after the duty has processed all items, we have new results. With this configuration, we achieved better performance, having an acceleration factor of over 1.5. As I said, this is the effect of making fewer context switches between sending and receiving within the test bench. The same configuration used for the streaming router with a mathematical block, the AES encryption block, leads to even better performance. As we can see, the acceleration factor is now almost 2. This increase is due to the rising of complexity regarding the emulated design. Because we've had the best results testing the streaming router with the AES block in the second configuration, we've decided to see the results for even more stimuli. Here, the acceleration factor does not have a constant decreasing or increasing behavior. This is because there are many factors that influence the TCP connection between the hardware platform and the machine that runs the simulator. The FPGA processing time, measured using this configuration for 10 million stimuli, is 36 minutes, which represents about 1/3 of the total co-emulation time. This brings me to the end of the presentation. To summarize the key points, when using OFC, there are several factors that you should consider in order to achieve a greater acceleration factor. Firstly, the number of DMA accesses should be limited to the minimum necessary if you want to achieve a better performance. Then, as we saw in the results presented, having less context switches between send and receive operations can also lead to an increase of performance. The acceleration factor is also linked to the complexity of the design under test. The difference between the co-emulation time and the simulation time will be greater as the complexity of the design rises. Therefore, you should consider using this setup or any co-emulation setup when verifying complex designs if the goal is to achieve a speedup. The OFC is a modular framework with two components that can be used together or separately. The first component is the OFC SystemVerilog Python, which can be used for communication between a SystemVerilog test bench and the Python environment. The second component is the OFC Python FPGA, which can be used for communication between Python and the programmable logic side of the PYNQ board. The two components can also be used together for achieving a co-emulation environment. And the last main point is that the framework requires little integration effort, can be easily updated, and as I said, it is open source and anyone can contribute to it. So, that was my presentation. I hope you enjoyed it. And if you have any questions, feel free to ask.